my research with the title Numerical Analysis of Stiffened Cylindrical Shells, a benchmark study. In here, I'm going to start. This is an overview of my presentation. I'm going to start with the background of the study, and I'm going to follow up with the research objective, followed by methodology, result and discussion, and I'm going to end my presentation with a conclusion. Here is the background of the study. Basically, Stiffened cylindrical shell structures are common panel compartment that have been widely used in many such applications for many years. This kind of application mostly can be found in offshore or submarine or aircraft or aerospace structures, nuclear and chemical power plant industries. Photos shown in my slide currently is a failed structure. It depicts a failed structure that can be found in many places in this world. Here is some background study. The problem about this sort of structure is, theoretically, when we apply this kind of structure, theoretically, let's say, for example, we apply a cylindrical shell, we actually compress it. Theoretically, you're going to estimate a kind of load, which is mostly we call it perfect load. But with the same shape, with same geometry and same dimension, we run it, experimentally, you're going to give a drastically lower than the perfect load. And this is the common issue or the classic issue for this kind of structures. And these differences or deviation is known as knockdown factor. And due to this deviation, there's a lot of studies that have been done, since the 1920s up until 1960s and up till now, to be fair. And more or less, this kind of differences is attributed to the initial geometric imperfection. And in industrial application, this kind of thing, they're going to apply the lower bound curvature, as we can see in the photo below. And this is more, we can say this is a industrial standard in dealing with this type of structure. So this is a bit of summary from the reviewed literatures. Basically, Stiffened cylindrical shell, there's not many update or not available experiment data up until this kind of recently there's not many available experimental data. Of course, not many, in previous literatures, there's no many studies that have been accounted to the influence of imperfection. And then, of course, this structure is quite complex structure, because you've got cylindrical shell and attached with it is a stiffness. Of course, you're going to impose with this discontinuity structure, and what will happen is you're going to experience a discontinuity stress and strain. And then, in overview of existing design guideline, there's an inconsistent estimation of buckling load due to the imperfection issues, and the variances in estimating the buckling load for cylinder is about 20 to 30%, and for cone is about 50 to 60%, as was previously reported. And of course, the big question is why the study is very important. The study is very important as it may reduce the structural strength up until 50% with this kind of imperfection issues. So, as it may reduce the structural strength up until 50%, then we need to avoid this catastrophic failure. So, this study can be aligned to the industrial significance. Okay, this, for example, let's say there's a new updated KDF, means knockdown factor. If there's a new or updated knockdown factor or design guideline is considered, it may help to reduce the material cost per structure, as if we more daring or using a much thinner plate and much light material. So the fabrication cost is expected to be reduced. For example, in order to mass saving, in terms of weight, assume that we got 1,000 kilogram mass saving in designing the shell structure, and then we presume that it costs about RM 10K per kilogram extra cash for thicker shell due to the safety reason. So production cost or the fabrication cost is going to be generate about RM 10 million. You know, we can save about 10 million per structure. Therefore, we achieve two things. You know, we save money, and then the safety aspect of the structure is still not jeopardized. That's what the whole things. That is about the whole study that is and is significant to the industry. So basically, this is a research objective of the study. Firstly, we try to evaluate the axial compressed or externally pressured stiffened cylindrical shell through finite element analysis. Second, we try to investigate and evaluate that focusing in the comparative study of initial imperfection to the current design guideline or current design standard. Here, as you can see, the selected method is the finite element method, where we use two ways of running it. First, we go by linear bifacial analysis, and then we go by nonlinear static risk analysis. And then for the imperfection, we select the SPLA. For the standard design guideline, for this case study, we go by ECCS, NASA SP 8007, and then EN 1993-1-6. And in here, as you can see here, the photo with A, the A photo shows a stiffened cylindrical shell with its boundary conditions and everything as we expected. At the end of the cylinder, we're going to fix it, fully fix it, and then in another end, we're going to apply a compressive load. Okay, and then at the midsection of the cylinder, I'm going to apply a little bit of perturbation load in order to trigger the instability. So this perturbation load is known as imperfection for the structure, because it's going to create a dent at the midsection. While the B photo shows the details of ring stiffener, the geometry one, the geometry of the ring stiffener, while the C show the geometry of the string stiffener profile and its variables. Here is some dimension and geometry properties of the analyzed model. Of course, we benchmark with 5 models that been tested experimentally by the previous researcher. So basically, we extract their data, their geometries, their materials, and everything, and simulate it back via finite element. And there is 3 types of materials that have been done in this study, where first is aluminum alloy 7075 T6, aluminum alloy 6061, and steel. Okay, so this is the result of the study. First one, we go by benchmarking and analyzing the collapse load. So we got three main things that need to be summarized. First, the collapse load estimated by the SPLA showed to be less conservative in nearly 10 to 30%. The deviation attained in comparing the experimental data distinguished to be 13% and 5% for each model for the case of external pressure. And the SPLA imperfection was considered. From here, you can see more or less the result obtained by using SPLA. It's much closer to the experimental one compared we run it via linear analysis of linear eigenvalue. It's very high, not slightly, it's drastically high in comparison to the experimental load. And then of course, if we make a ratio between experimental load and the collapse load, then we're going to produce a knockdown factor on the right column of the table. From the top table show the actual compressed the result of the actually compressed shell, while the bottom table show the result of the externally pressured shells. Here are some results where the photo A depict sensitivity studies of Y1A shell and distributed nodal factors by the SPLA in ratio of B for R over T wall from 462 to 506. Okay, and then B with the ratio of RT wall 63 and D with RT wall R over T wall 267. So this is all the result being obtained, where of course B is under axial compression, and C and D is under external pressure. Okay, and this is a summarized result of predicted initial imperfection. Of course, we're going to compare the generated initial imperfection. Firstly, we calculated using the standard, the industry standard, which is ECCS and EN 1993-1-6. You can easily calculate it, and then we're going to compare how close it is with the experimental and how close it is with our simulation. So from here, it's a perform valuation, especially for AR1, for the model AR1, AR-1A and R2 models. It's quite close. And then of course the differences is quite obvious for the codes and the SPLA for this model 2 model. And then model 2 is presumed to be incomparably sensitive to the other and too vulnerable for buckling incidents. And the code appeared to overestimate in local DEN in contrast to the SPLA and given expected data except for R2 model. And here is a what you call that? It's a study on seeing the variation, on seeing the structural dynamic response of Y1A Stiffened that been done via SPLA. As you can see, typical responses demonstrated by Y1A for the case of compression, where the event is associated with structural dynamic response indicated by 4 stages. As you can see, the first stage, it goes by initial buckling, slightly have some dented here, maybe 2 or 3 dented. Then it goes abroad up until local snap through, where at this point we can presume that, or we can estimate that somehow the structure start to lose instability. And when it begin to fail, it reached the peak load, where we call it global buckling. And in here you can see the reddish color and slightly yellow and green color is indicate where the structure started to deform and progressively deform once it reached the global buckling phase. So that's why come with M equal to 9 and N equal to 1. So in conclusion, we can summarize that the imperfection analysis on actually compressed and externally pressured Stiffened Cylindrical shell using the SPLA through the finite element simulation and international codes were presented. The collapse slope estimations made using the SPLA were shown to be in reasonable agreement with the published experimental data. The SPLA seems to be demonstrate an effective ability for designing an imperfection in actually compressed and external pressured Stiffened Cylindrical shells together with its estimated local dent. At some point, the SPLA appeared not to be the worst structural imperfection for some cases. The finding also highlight a small limitation in calculating the local dent via codified formulation. Thank you.